Now, the Clausius-Clapeyron equation is a modification of the Clapeyron equation, which takes into account the fact that the volume of a gas, when a solid or liquid turns into a gas, the volume of the gas is much larger than the volume of the solid or liquid. Okay? So, in other words, your delta V in the calculation of the slope is approximately equal to the volume of the gas, because you can ignore the volume of the liquid or the solid compared to the gas. Let's clarify that. Remember 1 mole of water. How many grams is a mole of water? 1 mole of water. So how many grams? You remember? 18 grams, about 18 grams. So how many mils would that be? Liquid water. What's the density of liquid water? 1 gram per mil. So that's about 18 milliliters, right? But that's if that's a liquid, right? Now, if you turn your water from liquid to vapor, water vapor, gaseous water, 1 mole of a gas would have a volume of how much at STP? 22.4 liters per mole, right? That's 22,400 milliliters. How does 22,400 compare to 18? Much bigger, right? In fact, if you only have 3 sig figs, 18 is not going to matter. It's like a drop in a bucket, right? So your volume changes a lot when you turn your liquid or solid into a gas. And so that equation that we had earlier can be simplified into this form right here. So this is the equation that describes, okay, remember your phase diagram? This equation right here describes this curve right here and that curve right here. This delta H for this curve will be delta H of vaporization, and for this curve down here, your delta H would be delta H of sublimation. Okay? So any 2 points on the curve, natural log of pressure on point 1 over the pressure at point 2 would be equal to negative delta H over R times 1 over T1 minus 1 over T2. So this is just an equation that describes this curve right here. So this will allow us to actually do some calculations, like how much does the vapor pressure change if you change the temperature, okay, or how much does the boiling point change if you change the pressure. Okay, so here's an example. Estimate the pressure inside a pressure cooker when the water temperature is 121 degrees. Delta H vaporization of water is 40.7 kilojoules per mole. So you use the Clausius-Clapeyron equation here, okay? So you're looking at this point right here. So at 1 atmosphere, we say water boils at what temperature? 100 degrees Celsius, right? That's 373 Kelvin. Now, if you want your water to boil at 121, okay, 121 degrees Celsius, what would that pressure be? Okay, that would be the pressure you need in your pressure cooker. So how would we solve for this? We say ln of P1 over P2 equals negative delta H of vaporization over R 1 over T1 minus 1 over T2. Okay? So what numbers do I plug in here? I can say that when T2 is 373 Kelvin, my pressure is 1 atmosphere. Okay? And so the question is, if T1 is, what's 121 Celsius? What's that in Kelvin? 121 plus 273, 394. So if T1 is 394 Kelvin, what is P1? Okay, and I'm given the delta H vaporization is 40.7 kilojoules per mole. Okay, so I know everything here. I can solve for P1. R, what's the value of R? for consistency, since my unit here is kilojoules per mole, I have to write my R in kilojoules per mole. R is 8.314 joules per Kelvin per mole. So, okay, for consistency, what I need, I'll change this to joules. So, 40.7 times 10 to the third joules per mole. And R is 8.314 joules per Kelvin per mole. Okay, so you plug those in, you'd be able to solve for P1. How would I solve for P1? I'm going to say ln of P1 minus ln of P2. Remember this identity for math? ln of x over y is the same thing as ln of x minus ln of y. Okay, so ln of P1 minus ln of P2 equals negative delta H over R, 1 over T1 minus 1 over T2. Now, I know this number. I can just plug in all the numbers I need there, right? So what would that number be? Negative 40.7 times 10 to the third joules per mole over 8.314 joules per Kelvin per mole. So moles, joules per mole cancels out. So that gives you Kelvin times 1 over 394 Kelvin minus 1 over 373 Kelvin. So your Kelvin will cancel out. So that's ln of P1 minus ln of P2. What would that be? Okay. 1 divided by 394 minus, open parenthesis, 1 divided by 373, close parenthesis, equals times 40.7 times 10 to the negative, 10 to the third divided by 8.314. That's negative times negative, so that becomes positive 0.6995. Okay, so that's ln P1 minus ln of 1. What's ln of 1? Or here, let's just make that ln of P1 over 1 atmosphere. Okay, it's equal to that. So you can say then that P1 over P2, which is 1 atmosphere, is equal to 0.6995. Oops, sorry. Take the inverse log, right? So e to the 0.6995. So that would be 0.6995 inverse log. So inverse e to the x, that's 2.012, 2.013. Okay. And so P1 is equal to 2.01 atmospheres. Okay. So that's assuming I got all my numbers right. You see, you expect the pressure to be higher inside the pressure cooker. Okay, let me just verify those numbers for you. Okay, 1 divided by 394 minus, open parenthesis, 1 divided by 373, close parenthesis, equals that times 40,700 divided by 8.314. Yeah, negative times negative 1, and then inverse log. Okay. solids. We're gonna talk about that next time.